Okay, welcome back. Today we stop developing new theories and new material, and we concentrate on making some visual application of whatever we've done so far. And we put, if you want, hands into the mud and try to play around with the concepts. And we do that by playing around with a simple code that solves the problems of understanding kinetics in a double well potential. And specifically, the potential we are interested in is one with a quartic potential. Now, where x naught is equal actually to minus 1. Now, this this quartic potential has interesting advantages because it basically you can tune by varying u naught the height of the barrier in units of kt, and you have a 2 metastable state. And this is a standard problem we always face in quantum mechanics, because it is the ground for discussing two-level systems, it's the ground for discussing tunneling events, and blah, blah, blah. So it's a standard problem people look at in theoretical physics. Now we look at this problem from the point of view of diffusion rather than quantum mechanics. But as we shall see, there will be very, very important analogies, and in particular there will be an inspiring, at least to me, inspiring analogy between the phenomenology of tunneling transition in a double well in quantum mechanics and the phenomenology of thermally activated processes in the same potential. So let's just begin by making a general overview of what happens in a double well in quantum mechanics. If you're in quantum mechanics, you know that your wave function in one of the wells is no longer an eigenstate of the Hamiltonian, nor is the wave function in the other well. But what typically happens that due to the presence of a finite barrier, there is a little bit of overlap of details, and because of the overlap of details, in quantum mechanics, the spectrum gets gapped. And basically, you have a spectrum of frequencies which more or less depend on the height of u naught, but most importantly, if u naught is large and produce in some units that somehow relate to h bar, I don't want to go into that discussion, there is an exponentially small gap between the ground state and the first excited state, with the relationship lambda 1 minus lambda naught divided, say, by lambda 2 minus lambda 1, much, much smaller than 1. This is what happens in quantum mechanics. And typically, this gap signals the fact that you can picture that as imagining that tunneling events are rare events. How do I know? Because if I construct a quantum propagator in quantum mechanics, which corresponds to, say, I'm on the left side of the well at time naught, and I wonder at what time I'm found on the right time of the knot of the well, for instance. Well, this can be seen as the ground state wave function at x naught, ground state wave function at negative x naught, times lambda naught over h bar t plus psi 1 x naught star psi 1 negative x naught e to the a h1, sorry, a lambda 1 over h bar over h bar times t plus blah blah blah. Now, as we discussed several times, all the eigenvalues that enter on the right-hand side of this equation, in this knot, they have much larger frequencies, therefore their interference is much more dramatic. And so basically when you add them up, you end up random numbers and random complex numbers. And if you want to think about the generalization of central limit theorem, but they would basically interfere out to zero. So when you go ahead and construct the probability by squaring the propagator, you're basically being dominated only by these two terms. You can neglect all the others. And what you get Rabi frequencies, Rabi oscillations, the typical oscillations of two-level systems. And the time scales, which determines how often you see oscillation from left to right, is controlled by the difference of lambda 1 minus lambda naught. And that's why normally, in units of h bar, of course, normally the gap between the ground state and the first steady state in tunneling problem is referred to as the tunneling rate. So in quantum mechanics, you have, in the presence of a large energy barrier, you have a very, very low tunneling rate. And in fact, you can show that if you increase the barrier, then you exponentially decrease the difference between these two eigenstates here. And as a result of which, you exponentially increase the inverse tunneling rate, or if you want, the time you have to wait until you see a crossing barrier event in quantum mechanics. Of course, you never see a crossing barrier event in quantum mechanics because you never see a particle under the barrier crossing. What you see is you have to wait long and exponentially longer time for building up a probability on the right-hand side if you start with a probability entirely concentrated on the left-hand side. Well, that's in a couple of words the discussion of Rabi oscillations in quantum mechanics for a two-level system. Now we want to move on to the problem that we are facing today, that is thermal oscillations in a two-level system. Now we have exactly the same potential. Okay, let me move this down. But this time, the particle is classical. Well, of course, if the particle is classical and I put it on the bottom of the well, the probability of finding it on the right of the well, in the absence of any thermocoupling, is zero. Because the only equation of motion for a particle with zero kinetic energy sitting on the minimum potential energy is I stay there forever. Of course, we are not interested in this problem. We are interested in the diffusion problem. And in the diffusion problem in which I have a temperature. So let this be the typical 1/2 kT thermal energy. And I want to choose this to be much lower than the typical energy gap. Now, under this condition, the particle violates conservation of energy and explores typically a region of energy kT. And if I expand to quadratic order my potential around these points, I can approximate this local equilibrium distribution with the solution of the corresponding eigenstates, zero modes eigenstate of the Fokker-Planck equation, that is the Gibbs distribution in the harmonic oscillator locally. But every so often, a particle gets a number of kicks in the right directions, gets to the transition state, and then rolls down to the right-hand side. And so what I expect is that if I start off with my distribution entirely concentrated here, I put many particles here, and suppose they don't interact. I get all of my initial distribution here, and I see how this distribution should evolve in time. Well, after some time, my new distribution will start build up a little bit of distribution on the right side. Because every so often, arguably very rarely, and we'll come to that. How rarely will be discussed later on in the course, but arguably very late, I get a lucky sequence of events in which the particle gets kicked in the right direction sufficiently many times to reach the transition state. And then at the transition state, it basically throws a coin, and with 50% probability it rolls on the left or on the right. That's a good definition of transition state, as we shall see again in the course. And if you get the right head rather than cross, you roll down to the product state, to the right-hand side. And so you have a certain probability. The more you wait, the more likely you are to have observed one of these unlikely events. Right? So we expect that the evolution of probability in this system to be something like I start from this, and then I will get a little bit of this, and then eventually I will even up. These are the two probability distribution in the two sides of the well, so to say, right? It's very bad drawing, but you got my point. And if I wait long enough, I will only have the Boltzmann distribution, and in the Boltzmann distribution, the probability distribution is obviously symmetric because the potential is symmetric, and the Boltzmann distribution is just the exponent of the negative potential in units of kT. So if the potential is even under reflection around the x-axis, then so will be the Boltzmann distribution, which simply corresponds to the fact that I put all of my particles on the left, I heat up the system to some level to give it some thermal energy, I go take a coffee, spend a day with friends and play guitar or whatever, then come back, and if the time scales in which the fluctuations across the barrier is smaller compared to my day, then I expect the system to have thermalized, to have reached the Boltzmann distributions in which all the particles are evenly distributed right and left. That's the thermalization process we discussed in math in the last several lectures, and we now want to see if this sort of qualitative picture can be seen in action by solving things numerically and see if things do what we think we do. But before we do that, let me tell you a little bit on how. So let me address a couple of questions. First of all, how would the dynamics of a single Langevin trajectory look like in a double well? Well, according to the discussion we just had, we start from a x naught negative 1. So that's negative x naught. This is x naught. And if I put my particles, say, here at time naught, here, and I start exploring here, what's going on if this is now time and this is position is that my trajectory will start doing this. Oh, and of course it doesn't go back in time. This is just forward in time. Occasionally it will go close but not quite make it, and about once every twice it gets close to the transition state, the coin flips to the right direction and you really make it to the other side. And then you keep on going, you keep on going here for a long time. So this time here is that, on average, is called the mean first passage time. And we will estimate it later on in the course, but we can give a rough estimate how long it is already at this level. We will, there's a well-famous rule, equation, that's called the Kramer's Arrhenius formula, which tells you that the typical time it takes to cross the barrier on average, the mean first passage time, is exponentially long in the barrier in units of thermal energy. That's the Arrhenius part, and the Kramer's contribution was to estimate this T naught, and it turns out that T naught, which has an explicit formula in terms of curvatures and second derivatives at the barrier and at the valley, which I will not give in this lecture. The important issue is that typically this is a time comparable with the local thermalization time. So what this formula really says is that there is a local thermalization process in which the system starts from an arbitrary distribution and very rapidly, say this distribution, which is certainly not even an equilibrium distribution in the left well, but very rapidly converge to a local distribution in the left well. And that occurs over the time scales which we estimated for an harmonic oscillator. So in the approximation which this is really an harmonic oscillator, you're neglecting the non-harmonic contribution that come at the level of the barrier. Well, we can estimate this time scale, and it's basically very close to this T naught. So very quickly the system collapses down to a locally Boltzmann distribution, but this is a quasi-stationary distribution because every so often particles leak out to the right-hand side of the barrier with a rate that is given by the inverse of this time. Or stated differently, the times of leaking divided by the time of local thermalization is exponentially long with a barrier. And you can generalize this to free energy barriers for multidimensional systems. This is not the purpose of the present lecture, so I will not go into that. Okay, that's the phenomenology of it, and let's see if my theory will account for that, and to what extent Fokker-Planck dynamics will account for that. And in addition to that, let's see if I can solve this numerically with a simple code and see whether the code will return results that are in agreement with what we sort of expect from these general algorithms. So let's move on. So the Fokker-Planck probability to find the system on the right-hand side at time t, provided you started from the left-hand side, is given in spectral decomposition by the right-hand side eigenvalues at x naught, left-hand side eigenvalues at negative x naught times to negative lambda n t. That's what we learned over the last couple of lectures. Now again, in the limit, if it is true that the spectrum is still gapped, then we expect this to be dominated by only two eigenvalues. The Boltzmann eigenvalue and the first excited state. Now remember, this is the Boltzmann distribution. This is 1, and this is 1. So basically, what you get is like Boltzmann of x naught plus corrections which scale down with lambda 1 t. So first of all, the question is lambda 1, can we understand why lambda 1 minus lambda naught is really much smaller than lambda 2, say minus lambda 1, either for diffusion? Well, I can approach this problem in two ways. I will approach first the mathematical way, the correct way, and then I will also give a sort of a heuristic explanation for that. So in order to see the mathematical answer to this question, so in other words, is the spectrum of the Fokker-Planck operator still gapped? Just as the spectrum of the quantum mechanical operator for the same double well was gapped because of the rarity of tunneling. Well, we exploit the formal connection between diffusion and imaginary time quantum evolution. So in other words, it is convenient. Remember, the spectrum of the Fokker-Planck operator is the same as the spectrum of the effective Hamiltonian. So if you can understand the spectrum of the effective Hamiltonian, then we can transfer this information on the spectrum of the Fokker-Planck operator. So this is a good thing to do both for analytic considerations and for numerical consideration. And the reason is that the effective Hamiltonian is Hermitian. And whenever you have an Hermitian Hamiltonian, you have a lot of simplifications because of the properties of the spectrum and the number of independent entries on the Hermitian matrix and all that. So how does the effective Hamiltonian look like for a thermal diffusion problem in a double well? Well, what you have to do is to write the standard diffusion term, which is a one-dimensional Laplacian, also called second derivative, plus an effective potential. And the effective potential, let me write it again, contains a gradient square negative a temperature with the Laplacian, which again, gradient and Laplacian here as just simple derivatives. Now, how does this look at all? Well, let's first take the very, very low temperature limit. In the very, very low temperature limit, the effective potential becomes extremely large because of the temperature downstairs. And in addition, in a very low temperature limit, this part can be neglected. So if I look at this, if this is my physical potential U, well, the effective potential looks a little bit like this. Anywhere, if I first of all take the effective potential to be d over 4kt squared times u prime squared, I'm neglecting the Laplacian term, then you see the potential is positive definite, and it's zero everywhere I have a stationary point of the potential. So it's going to be zero here, but also here, and also here. That's my effective potential. So it doesn't quite look like the potential energy. Well, it does have barriers, but it has more barriers, if you want, than the physical potential. Now, what happens if I now begin to include a little bit of curvature? Sorry, a little bit of temperature. Well, that means that in the presence of temperature, and I keep kT finite now, this becomes this negative 2 kT u double prime. Now, the sign here is negative, and you get different contributions whether you are in the minimum or you are at a maximum. You see? Because the sign of the second derivative term will flip if you are in the minimum or in the local maximum of the potential. So that means that basically here you're going up. Sorry, I just said something wrong. I meant here I'm going down, because you see in a minimum this is positive, I'm decreasing the effective potential. And here I'm going up. Now, if you plug in normal numbers, as long as the U naught is, say, 5, 6 kT, you realize that it's basically quite a dramatic effect. You immediately something like this. You see something like this. To the point that it's quite rapid, since the second derivative here is stiff in a quartic potential, you very rapidly come to a point where you completely killed the barrier in between. But there's going to be, in this case, so-called phase transition. Whenever a minimum, well, it's not really phase transition, this is a finite system, but you have a change of regime whenever your energy landscape changes qualitatively. But the point that I want to make is that at finite temperature, quite soon, the potential looks like something like this, the effective potential. So the problem of understanding the gap is the spectrum of the diffusion in the double well becomes at finite temperature, say when the barrier is a few units of kT, becomes equivalent, let me draw it again a little bit better, to the problem of a quantum mechanical problem with something that is slightly modified two-state system. Of course, this is supposed to be symmetric around the x-axis, and my drawing is not quite good enough. Okay. So, at the qualitative level, if this barrier is not large in terms of kT, and typically it is not for this system, then at qualitative level I expect this to behave like a two-state system in quantum mechanics, and since we know that two-state system in imaginary type quantum mechanics have a gapped spectrum, also the diffusion problem will have a gapped spectrum. So you can think about this as a semi-rigorous or semi-heuristic. I don't quite care about how you want to define it, but it's a good motivation to see that you have a gapped spectrum and you have a slow relaxation in the presence of barrier. But physically, this is good mathematically. For the most mathematically inspired people, they like the analogy with quantum mechanics. They enjoy seeing the relationship within the spectrum, and they can get convinced that indeed thermal relaxation is slow in a two-state system. But for the most physically inspired guys, they want to see why this is happening. Let's estimate if the thermal relaxation should be rare or not. Remember, in order for the particle to be able to cross the barrier, we mentioned that a very rare event must happen. The particle must be pushed in the right direction for a string of times, for a right sequence of time, because on average you get as many kicks on the right and as many on the left, and you stay close to here. You get a kick on the left, maybe two, and then you get one on the right, and so on. You keep on moving here. But every so often you get kick on the right, kick on the right, kick on the right, kick on the right, and then you're down. So if you ever played any dice game, like when you have your little duck that has to go around a path and reach a target, and every so often you get an obstacle that gets you back. It's called the gioco dell'oca in Italian. You discover that every so often, since these games take forever, and you have to do them if you have children, it can take an hour because you get close and then you get to roll back. You get a good statistics on rare events on your dice. And you will discover if you play for an hour, maybe it will happen 3 or 4 times that somebody gets the same number, say number 6, 3 times on a roll. Why? Because, the possibility is 1/6 to the third. And 1/6 to the third is something like, I don't know, 200. And I don't know, 6 to the third, what is 6 to the third? 6 to the second is 36, times 6, it's roughly 200. So if you play dice 200 times, then on average you get 3 times 6 on the roll. And if you ask, how often do I get any number on the roll 3 times? Well, you have to multiply this probability by 6, and therefore it's 1/36 attempts. So you see, that's the kind of things that happens. So now let's make a very simple model. And the model is one in which anytime I get a kick, I can get it either on the left or on the right. And anytime I get a kick, I move by kT. Well, I know it's an admittedly oversimplified model, but it will catch the idea. So how many kicks on the row on the same direction I must get in order to cross a barrier? So anytime I get a kick, I have 1/2 probability to get a kick, right? So basically what happens is I have to, in order to cross a barrier delta U in unit of KT, that's the number of right kicks on the row I must get to go from here to there. And so that means that if I throw my dice every tie knot, and then each time I have a probability that's 1/2 to this power, so that means that the times I have to wait is roughly 2 to the delta U over KT. Now, this is an admittedly very, very, very rough estimate, but it gets pretty close to the e to the 2 U times divided by KT, which is the right result. We are missing a lot of physics. For instance, we could get 4, then 1, then 3, and I'm still getting on the other side, right? Or I don't always get a kick by KT. I sometimes get KT fractions and all that. And if you do things correctly, what happens is that you get an E here rather than a tau naught. But E is 2.71, and with this extremely crude model, we got on the right mark, roughly speaking. So yes, even on the physics ground, on the probabilistic ground, we understand the relaxation time should be much longer than any local equilibration time, which is stated differently. Lambda 1 minus lambda naught should be small compared to lambda 2 minus lambda 1. Okay? Okay, so that's it. That's what we expect to see. Now it's time to go back and do some numerics. So in order to do that, I have restarted and restored, if you want, an old code of mine. And I apologize with everyone for being a dinosaur, since this code is still written in Fortran 77, which probably for most of you sounds like when I was a student, when people were telling me they're using the Regulus. It was this mechanical object they were using to do calculations. My father used to do that, to do calculation with a mechanical object. So, but I think it's transparent enough for understanding what's going on. So I'm just gonna go through the code just to let you understand what the code does, and I don't care about the details of how a Fortran code is set up. Basically, you have to declare your variables at the beginning, vectors, linear. This is more or less the same for all problems. Now, as you can see here, I'm choosing distances from negative 1.5 to 0.5. The idea is to not just stop at the minimum position, which is negative 1, but to go a little bit further just to see that you get the exponential tails going down. Now you have a dimensionality and L, and the reason these two parameters are there, they are relics, because this code was taken from another code I had for the harmonic oscillator, for the hydrogen atom wave function calculation. And there, of course, you have this fact that you use the central potential and you reduce a three-dimensional problem to an effective one-dimensional problem in the radial potential, and then you have all the solutions with different values of angular momentum, right, for the radial wave functions. And so I should erase these actually, but basically what I was doing there, I was putting myself in the case in which instead I was really doing the real one-dimensional problem for a particle in a one-dimensional potential. Now here is where I define my potential, and as you can see, my potential has a U naught of 1, but then I have a temperature beta that is 1 over 0.25, which basically corresponds to saying that if I set the Boltzmann constant to 1, I have a temperature of 4. So in other words, 1/4. That means that basically the height of the energy barrier is 4 times the thermal energy, which is good enough for being thermally activated. The reason I don't choose 1/1000 is that when you get to very, very, very large barrier, then the exponential gap becomes small and you very rapidly reach machine's precision. And also because if I have some time later, I would like to solve the same problem by integrating the Ito rule for Langevin dynamics explicitly and seeing the transitions in Langevin trajectories. And if I choose the temperature too low, it would take me an exponential long time on my computer, and at some point I would run out of computer time, even for such a simple problem. So 1/4 is a reasonable time because the exponent e to the fourth is a reasonably large number. And being large, it means that exponential effect will be distinguished from, say, polynomial effects. Okay, now what you see here, you have an if checking step, which I basically try to avoid plotting anything that goes further than negative 1.5 and 1.5, simply for avoiding my plots to be dominated by the very large part and the tails for the potential, and then you don't see whatever happens in the interesting region because the quartic potential grows very fast. So I just want to, this is just an artifact to plot only the part where you see really the shape of the potential. Now, next thing, I want to evaluate the effective potential. I can do it two ways. Either I explicitly write it. This is where after you do the derivative, and after you do the derivatives, and then you evaluate the effective potential. I choose a slightly different ways that I find a little bit more physically transparent, which is evaluating the force term, the gradient square term, and the Laplacian term numerically. As you can see, this is the discretization formula. First of all, because for a one-dimensional system it's very simple to do that. But then if you do that, then you see that the effective potential looks familiar. He has this d squared over 4 kt squared. The diffusion coefficient is set to 1. And then you have gradient square minus 2 kt Laplacian. Beta is 1 over kt. Right. So this is really the structure of the effective potential. And then, what am I doing here? Oh yeah. Here I'm simply saying that if I'm getting close to the minimum, there I'm setting equal to whatever. This is probably something I don't need. This is the non-unitary rotation term which you need to relate the Hermitian to the non-Hermitian term formulation of the diffusion. This is the famous e to the negative beta half u that you need to go from Hermitian formulation to non-Hermitian formulation. So what I do here, I write the force term, the unitary term, and then the effective potential. So we can look at the effective potential and see if it looks like as we have imagined and described. Now, this is the part that comes with which you need to solve really the eigenvalue problem. So basically the idea here is to map the problem into the Hermitian problem, diagonalize numerically the Hermitian Hamiltonian, and then use the non-unitary transformation Wi to reconstruct the left and right eigenvalues with the prescriptions that we used in the lectures, that we defined in the lectures. So now let me go back on the screen for a moment. Okay, I want to just say something. You probably are all familiar on numerical solution of the Schrödinger equation for 1D, for simple problem, but let me just review how I do it. Well, basically, I'm putting things on a mesh. So this is my potential, I discretize, and I allow my particle to sit only on the mesh. Then if you do that, a function is just a vector, because it's a set of points in a, if these are, say, 2n points, 2n plus 1 points, my function is defined by the, or my wave function, for instance, let me call it psi, is basically a vector made up by 2n plus 1 components, because it's the value of psi in each of these points. And then when I look at the second derivative of my function, well, that's, let's forget about the diffusion constant for a moment. That's that you can write it in the usual discretized form. I think you are all familiar with this. So basically, this is a matrix which contains band structures, basically band matrix, band diagonal matrix with nearest neighbor terms here coming from here, and this is the diagonal term, and 0 everywhere else. And then if I add to this the effective potential only acts, it's a diagonal operator in position space, so basically only enters in the diagonal terms of the matrix. Well, you don't need me to write this, it's quite clear. So, as usual, quantum mechanics is defined on the Hilbert space, but if you discretize the Hilbert space on a mesh, the Hilbert space reduces to a finite dimensional space, that is to a linear space, to a vector space, in a dimensionality which is dictated by the number of lattice points you put in the mesh. In this case, this is the number of lattice points I put in the mesh. So all you have to do is to diagonalize this matrix. And you'll get vectors, eigenvectors. This will be my solutions. And after you have this eigenvector, you multiply by these weights. And you will get the right eigenvalues. And if you multiply by the inverse of that, you get the left eigenvalues of the Fokker-Planck equation. So more or less, that's how the code works. And now we go back and see how that is translated in our Fortran code. That's where you define the kinetic energy, and you add to the diagonal term the potential everywhere you see. In the off-diagonal terms, you don't have potential, as you expect. Whenever you see a red script here is because we are commenting our lines. That's how you comment lines in Fortran. Okay, so then what I do here is I call the subroutine the diagonalize, and I'll not discuss how the diagonalization is done in this subroutine. You can find that in the literature. And what this subroutine will take an Hermitian operator, give me back eigenvalues and eigenvectors, and I stop to the first 6 eigenvalues, because as you go up, then the numerical accuracy gets harder and harder. So once I do that, I construct the left eigenvalues and the right eigenvalues by multiplying by W, the root of Boltzmann, and divided by right value. There is a negative sign here simply because quantum mechanics doesn't care about signs, because the wave function is defined up to a phase, and by pure numerical accidents they will return me the negative solutions, and my probabilities have to be positive definite, so I have to flip them sign. This is just a coincidental accidental fact. For quantum mechanics, wave functions are not defined up to a sign. And here you see, so are defined up to a sign, only up to a sign. This is the current defined from the continuity equation. And then here, what I do is I evaluate I consider, now what I do here is I print out my Hermitian wave functions, my right eigenvalues for the first 4 excited states, ground state and 3 excited states, my left eigenvalues for the first ground state plus 3 excited states, and then I reconstruct the conditional probability to start from a point which I define to be 42. 42 is basically the point where the particle is at -1, you will see, to be found on the other side to be found at position R after some time t. And I choose the time t to be twice the gap. You see? So I choose the time to be just twice as long the difference between the inverse between the second excited state and the first excited state, which is basically I'm choosing to work in the condition where I'm supposed to be right in the gap, where I should be seeing some rare transition. So this is done because in this time regime, I expect my probability to look like this. I'm going to show it in a minute. To be dominated by the, I start from here, at time naught, this is entirely here, it's a delta function here, time naught. And I expect after this time to have built up a little bit of probability also on the right hand side. And let's see if this is actually what goes on in the code. So let me compile the code. So this is the instruction for compiling the code, and obviously there's an error here. So let's go and see what's the error. Ah, yeah, there's a missing parenthesis here. So let's go back on that. Let's compile the code. There's still an error, and I guess the problem is okay, there's a one extra parenthesis missing here. Okay, this is here, and this is here. Okay, now it should be compiling, hopefully. No, and I guess let's see, I wonder whether this should work. It should be working. Come on. Now it's working. Fine. It's calculating the spectrum. Takes some time because I used many points. Okay, so let's first of all look at the spectrum. Let's look at this. First of all, here we see that the difference between the ground state, the ground state is not exactly zero. Well, it's not exactly zero because we are not really doing calculation properly. If I were to do calculation properly, choosing many points and blah, 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 then this should be the Boltzmann distributions who have a zero value. But you should compare this number to the other ones. I choose the number of lattice points and blah, 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 so that I can do calculation in a couple of seconds without losing time. If you do properly, as you increase the accuracy of calculation, you can show that this guy goes to zero. The other important thing is that this difference between this excited state is very small, comparable to the error you're doing on the first. So it really is an exponentially small term. And in fact, from the second to the third, you see there is a full range, full order of magnitude, actually 2 orders of magnitude. So yes, we are in the same situations in which the spectrum is clearly gapped. And now we look at the conditional probability for starting from a point minus 1.34. Why that? Well, just somewhere on the left-hand side. And after a time that is twice this gap, this inverse of this gap, then this means that the exponent that I need to put in the first excited state, so this is right naught, left naught, plus right 1, left 1, e to the minus lambda 1 t. This exponent here will be 0.85. So my combination would be this with this given by 0.35. 0.85. But why? I chose that just because it's a convenient number to do calculation. As you can see here, that's exactly what I put here. Okay, so let's time to look at the results. I use XMGR to plot things. Let me go here and plot. Okay. Let me import data. Let me first look at the potential. If I have it, yes, there we go. No, that's, I clicked on iTunes. A mistake. Okay. So the potential is the double wide potential, no big surprise. Let's look at the effective potential. If I have, yes, I should have it somewhere. If I don't, never mind. No, I don't. Fine. I don't care. So let's look at the right eigenvalues. You see? Boltzmann distribution. Let's look at the second eigenvalue. So this is the way we do is by blocking, and I take the second. Let's see if this is, no. Yeah, this is the first excited state, and just in complete analogy with what happens with the double weld problem in quantum mechanics, the first excited state is an antisymmetric combination of the welds, and that follows from the fact that basically this is very close to a standard problem with effective potential in quantum mechanics. And then if you go forward and you plot additional terms, you discover that excited states, of course, have more nodes. See, now this is not very visible in yellow, unfortunately. Let's see if I can change the color. Let me go violet, sounds like a good color. And then if you were zooming here, you will see there was one more node, because, you know, there's a principal quantum numbers and all that. Okay, so let's look at the conditional probability. Let's look at the conditional probability. So let's cancel everything and look at the conditional probability after a time starting from complete left to be found on any other point after a time twice the inverse of the gap. So let's apply this. And as you see here, it looks exactly like we saw. Very rapidly we have converged to a Boltzmann distribution on the left, but with a little bit of a tail on the right. That's the leak out that I was referring to. Okay, I think this is quite instructive, and I think it's I think you could see in phase all the concepts that we've seen in formulas so far. It's very simple to work out with Python, for instance, a code that does what I've done in Fortran here, to play around with these concepts. Maybe the last thing I want to show you before I close up is how the current looks like. And that's quite interesting. The current looks constant across the barrier. And we'll come back to the fact that having a constant current across the barrier later on in the course. But I will comment on that. Basically, once you have a current of particles committed to get to the other side, this is the current calculated from the conditional probability, then of course all particles that live on the left have to visit the right hand side, so they have to go through the barrier. So this is very different from the question, how often do I get to the barrier? Which is, of course, very rarely, so the points on the barrier are exponentially suppressed. But if I ask the question, what is the density of point in a current that goes through the barrier, then it's flat across the barriers, because the trajectories have to cross the barrier, essentially. But we'll get to the transition pathways phenomenology more in the future. I think this is a good time to stop. Goodbye.